Okay, gas laws. Probably some of the easiest chemistry we do, so I'm not going to go into great detail. The math is simple, the concepts are simple. We have 4 scientists shown here that are instrumental in the gas laws, but good news is you don't have to know any names at all. So, combined gas law is that P1V1 equals P2V2 over T2. So, pressure, volume, temperature. Only trick to knowing this is that temperature must be in Kelvin. Pressure and volume can be in any units. Boyle's law is the first one, and that one's that pressure and volume are inversely proportional when temperature is held constant. Charles' law is the second one. It says that volume and temperature are directly proportional and at constant pressure. And so V1 over T1 equals V2 over T2. Again, temperature must be in kelvins. Third one is Gay-Lussac's law. Pressure and temperature of a gas are directly related and provided that the volume remains constant. And so we have P1 over T1 equals P2 over T2. Avogadro's law says that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles at low pressures. And A is just a proportionality constant, just some constant. V is the volume of the gas, and N is the number of moles. The ideal gas law is a combination of all the gas laws, and it says that PV equals nRT, pressure is usually, and you should just get used to doing it in atmospheres, volume in liters, and N has to be in moles. R, you use gas law constant 0.08206 liters atmospheres divided by mole kelvins. Temperature has to be in kelvins. So, real gases are what happens. You don't need to know this equation, but you should be able to apply the concepts of real gases. And it says that at high temperature, small volume, and at low temperature, the attractive forces become important in gases. So you must adjust for the non-ideal behavior of the gases using van der Waals equation, which is shown here. And we have to correct both for the pressure and we have to correct for the volume to get an ideal pressure and an ideal volume. And so you see the nRT, or the left side of this equation, is different, but the right side of the equation is the same. So we correct for the pressure and we correct for the volume. You should be able to do these equations easily. So, not the real gases, but the ideal gases. Sometimes we want to know the density of a gas, and density is mass divided by volume. In the case of gas laws, we use the molar mass divided by the molar volume. So at STP, density would equal the molar mass divided by 22.2 liters, and we get the density of our gas. Pretty simple. Density for an ideal, using the ideal gas law, we've done a little manipulation, and I can show it to you in class if you need it, but we've replaced moles with molar mass, and we've replaced density with volume. Volume has been replaced with density, and we get that D equals MP over RT, and again, use the same gas law constant, temperature still has to be in kelvins. And molar mass will be in grams per mole. I have a few problems here for you. If reactants and products are at the same condition, temperature, and pressure, then mole ratios of the gases are also volume ratios. So here I have 3 moles of H2 plus 1 mole of N2 yields 2 moles of NH3. That's saying that simple enough, all in moles. But I could also say it all in liters, or I could say it in milliliters. So, how many liters of ammonia can be produced when 12 liters of hydrogen react with an excess of nitrogen? So now we're just asking you to set up a ratio. So we start, why don't you go ahead and try and figure this out? and I will display the answer. So you might want to pause this here so that you can figure it out and then check your work. Pretty simple though. So 12 liters of hydrogen ratio using our equation from the relationship between hydrogen and ammonia should be 3 to 2, and we should get 8 liters of ammonia. Next question. How many liters of oxygen gas at STP can be collected from the complete decomposition of 50.0 grams of potassium chlorate? First, you need an equation, and you have to balance it. After we have that, we're going to use a little stoichiometry where we start with grams, and we're going to go to liters of a gas. So we're going to start with grams of this substance, use a little stoichiometry to get to moles of oxygen, and then we're going to convert that into liters. So, and again, we're at STP. So at STP, 1 liter or 1 mole of any gas equals 22.4 liters. So pause the video right now and try and work this out. So start with our 50 grams of potassium chlorate. Molar mass of potassium chlorate gets us to moles of potassium chlorate. Our mole to mole ratio says we have 2 moles of potassium chlorate for 3 moles of oxygen. And then at STP, 1 mole of oxygen is 22.4 liters. When we cancel our units, we come out in liters of oxygen, and we should come out with 13.7 liters. Remembering that these moles in front here are counted numbers, so they are infinitely significant. Your number of significant figures comes all the way back here at your data. Okay. Next problem. How many liters of oxygen at 37.0 degrees Celsius and at 0.930 atmospheres can be collected from the complete decomposition of 50.0 grams of potassium chloride? Same question, but now we're not at STP, so we can't use 22.4 liters for 1 mole. So pause the video here, set it up, see if you can work it out. We are going to have to use what equation? You might want to figure that out based on what you're given and what you can figure out. So pause it here. So I have 50 grams of potassium chlorate. I want to get 2 moles of oxygen. So I'm going to use molar mass. I'm going to get to my moles of oxygen, and I'm going to calculate an answer here. And I get this many moles, 6.612 moles of oxygen. Now I can use PV equals nRT, putting in the information from the problem, and I get 16.7 liters of oxygen. Dalton's law of partial pressure is the last kind of problem we're going to work through. Dalton's law of partial pressure says for the mixture of gases in any container, the total pressure is equal to the sum of the individual gases. So this is used mostly when we're talking about pressure of gases collected over water. So that concludes it for this chapter. We will talk to you guys in class. Thanks.